For an object doing circular motion, we know we can describe it with the angular velocity, angular displacement, and angular acceleration. But now let's find out the relation of this angular velocity with the linear velocity. And here is the object's motion. So it starts at this position, as t equals 0 seconds. And there is also the reference direction for angular displacement. The object right now is at this location. So its linear displacement is r here, and the angular displacement is this theta angle. Now let's look at this arc length. We call this length s. Now the radius of the circular motion is capital R. So that's a relation we can write out between R and S. So S equals R times theta. Now if I take a derivative of both quantities, left and right side, with respect to time, ds dt equals, since R is a constant, so we just need to do derivative for theta, d theta dt. Now we remember that d theta dt is omega, the angular velocity along this direction. Now how about the left side? The left side here is the linear speed. V is linear speed equals the distance traveled, which is this arc length, divided by the time. Okay, and that equals radius times the angular velocity. That's the angular speed in this equation here. So that's the relation between linear speed and angular speed. And if I look at the velocity at this instant, then I'm going to draw a tangential direction. That's the v here. Okay. Now, if we look at the second derivative of this arc length, then we get linear acceleration, and the right side is the radius r times angular acceleration. But now this a, what does that stand for? Because for an object doing circular motion, it can have radial acceleration. It can also have tangential acceleration if the circular motion is non-uniform. And in this case, this a actually corresponds to a tangential. It's this at here. So a tangential can change the magnitude of the velocity, and a radial, remember a radial is called also centripetal acceleration, and it can change direction. Direction of velocity v, and this at, the tangential acceleration, changes magnitude of v. So that's why, because this second derivative here, meaning that it's the acceleration that changes linear speed, so we should use at here for this acceleration.